Thank you. Is it visible on my screen? Anyone? Can you respond something?
Yes, sir.
Okay, thank you. Okay, the 3D printing rapid prototyping, the definition itself, it is telling, okay, it is a technology that produces models and parts from the 3D CAD model data and CTR MRS scan data and model data creation from the 3D digital objective system. This definition is given by the Terry Holler. In this one, from this definition, we can conclude that we can make a product with using the 3D CAD model or CTR MRI scan data and whatever the data we are created from the 3D digital object system, that is called the reverse engineering data. With using these three data, we can make objects in the 3D printing, but here we require a intermediate connected file format is required from the design to the manufacturing. So that's why we require here STL file in the 3D printing software, in the 3D printing softwares as well as 3D printing machines. And now, okay, this rapid prototyping in 3D printing technology is transformed into the manufacturing. And now in the olden days, these 3D printing technology and rapid prototyping technology, okay, that are used only for the prototype purpose only and for the visualization purpose only. Now, this technology is using for the functional models. Okay, directly we can make and we can use in our application. So that's why we can now this rapid prototyping is named as additive manufacturing. Okay, after 20 years, additive manufacturing, 3D printing, rapid prototyping, digital manufacturing, solid free form fabrication, all are the synonyms of the 3D printing technologies. Here, the basic steps in the 3D printing, you can see this is a picture diagram how we can generate a model with using the 3D printing technologies. Here, this is a CAD model. Okay, I wanted to make a cup, this type of cup here. How you can make this one? Okay, which processes is required? Which sequence of steps are required? Now you can see in the slide. Here, this is a CAD model. Okay, this CAD model we are going to convert the STL file in the second step. Then this STL file we are sending to the machine with using the various 3D printing softwares. Then in this one, we are going to set up the machine parameters. Then based upon our slicing, okay, here in this one, we are generating the STL file. That STL file, when we are converting the 3D printing software, now the STL is converting to the slice information. Based on the slice information, whatever the inputs we are giving to the machine, it is taking based on the slice information and input information, the parameters of the machine, it is taking and then it is going to build a model here in the 3D printing machine. Thereafter, after completing the process, we are taking out from the 3D printing. When it is going to print, this model is sticking to the build plate. This is called a build plate. We are going to remove the model from the build plate, and we are going to remove the support structures. If any support structures are there, we are going to remove the support structures, as well as any post-processing techniques is required. If you wanted to improve your characteristics in the 3D printed component, that you can do it in the post-processing techniques. Lastly, we are going to use our product in our applications. These are the sequence of steps to create the model in the 3D printing technology. Here now you can see in the first one, it is we are going to deal the softwares. Even converting the STL file also, we are going to deal the softwares. Even file transferring, okay, the STL file directly we cannot give to the machine. The machine is taking the layer information. Okay, the additive manufacturing, the name itself telling it is a layer information. Okay, we are going to make a product layer by layer. Okay, the 3D printing, it is taking the layer information. Okay, based on the layer information, the machine is going to stack one layer upon the other layer. Lastly, we are getting our required object. So the from STL to size conversion, we require some softwares. Here in the machine build-up setup also, we are going to give the machine parameters with using the 3D printing softwares. Here, from near to 1 to 4, almost okay, from here to here, we require the 3D printing softwares. We require design softwares. We require conversion softwares. If any errors are there in the STL file, we are going to correct the errors in the softwares. Okay, from nearly half of the 3D printing process is going to deal with the softwares. So that's why this session is introduced for you, for your concept, for getting the concepts, how we are going to convert the CAD model to the slice information, how we are going to convert the CAD model to the G codes. Okay. Now you can see, okay, when we are going to see this one picture here, the basic steps, we are categorizing 3 processes. First one is the pre-process, next is the process, post-process. In the pre-processes, we are going to deal all the softwares here. Even design for additive manufacturing technique, that is also is coming under the pre-processing stage here. In the pre-processing stage, we have to create the design. We have to optimize the design. We are going to design as per our additive manufacturing. That's why we are calling as a design for additive manufacturing. And we are going to slicing the data, and we are giving the inputs for the 3D printing. All these things, okay, we are doing in the pre-processing stage. Here in the pre-processing stage, we require the softwares. Without software, without the CAD modeling technique, we can't do anything in the 3D printing technologies. Okay, after slicing, okay, the slice information, okay, the machine parameters we are giving to the machine. Then the machine, it is building the model. Lastly, okay, we are getting model. Here we are having, suppose some post-processing is required. Suppose I want to improve my surface properties. I want to improve my strength, improve like that. You can do in the post-processing with using various post-processing techniques. And if any support structures are there, that support structures also you have to remove it. Without support structures, we can't make a model in the 3D printing technologies in certain processes. Suppose in the powder based, even plastic powder based machines, we don't require any support structures. Suppose if you are taking the FDM type technologies, if you are taking the STL type of technologies, okay, we require the support structures. Even powder based metal machines also require the support structures. Without support structures, we cannot create the objects in the 3D printing technologies. So that's why, yeah, the support structure generation also is coming under the pre-processing stage. Okay, after generating the supports, you have to remove, that is coming under the post-processing techniques. Here, now from this one, we okay, the CAD, we are going to convert the STL file. Why STL file is required? Okay, so nowadays so many CAD softwares are available. Directly from the CAD softwares, we can't connect to the 3D printing machines. And nowadays so many 3D printing machines are available. The 3D printing, all the machines are not supported with the CAD softwares. So here there is a required one connectivity from CAD to the 3D printing. So that's why, okay, initially who is invented the 3D printer, the Chekhal, he is invented the STL file. Still now we are using a STL file, a standard file format in the 3D printing technologies. Okay, so many files are arised, but still now we are using the STL file for the 3D printing technologies. What is the STL file here? Now you can see here, this is a cube. When I'm converting this cube, okay, this total surface is tessellating by the triangles here. Now you can see here. In this tessellation with using the triangle, that is called, okay, that is called the STL, or that is called the stereolithography file format. The total surface is converted with the triangles. So that's why the STL file is also known as standard triangle language. Some people, they are calling as a standard tessellation language, because okay, this triangle is tessellated on the surface and we are getting the required file format. So that's why we are calling as a standard triangle language as well as a standard tessellation language. But okay, the 3D printed, the first 3D printing technology is a stereolithography machine. Okay, the first, okay, this file, they are initially they are used for the stereolithography machine, who is the inventor of the 3D printer. So that's why this, okay, this file named as a stereolithography file format. So all are the same, all are the synonyms. Don't confuse about these things. The STL file is a global accepted file format. Still now we are using the STL file format only. Here in the STL file, so many drawbacks are there. But okay, still now we are using the STL file because it is the simplicity of the structure. Yeah, how is the structure is there for this STL file? Now you can see here. With this triangle, when I'm taking this triangle, okay, it is having the three vertices. This one, V1, V2, V3. This vertex, okay, normally what we are calling as a points of the triangle. These points, okay, we are calling as a vertex in the STL file format. Here, this is a vertex V1, vertex V2, vertex V3. With using these three vertexes, okay, we are representing a one triangle. Here in the STL file, each triangle has a one facet normal. Already you know, okay, from this triangle, we can calculate the facet normal. Suppose this is a V1, this is a V2. With using 2 points, we can calculate the vector A. Suppose this is I'm taking as a vector A. With using V1, V2, we can calculate the A. V1, V3, V2, we can calculate the B. V1, V2, we can calculate the B vector. And V1, V3, we can calculate the A vector. With using the A and B vector, we can calculate the facet normal. A cross by B. When your formula is there, okay, with using this formula, we are going to calculate the facet normal. Okay, like that, okay, this each triangle is representing with the 3 vertices and one facet normal. The facet normal, it is always rotating the anti-clockwise direction and it is moving from the inside to the outside. Okay, this is a representation of the STL file. Yeah. Okay, the total STL file, okay, we are starting with the solid name and end with the end solid. In the between of this solid and end solid, okay, representing the each triangle information. In the one triangle, it is consisting of the facet normal as well as 3 vertices. These 3 vertices fixed in between of the end loop and outer loop. This is the structure of the STL file here. Okay, those who are doing the research, if we require the STL file, with using the STL file, we can develop so many algorithms. Okay, based on the algorithms, okay, nowadays so many publications also coming. Okay, this structure is required. Okay, the editing of the structure is required for to write the algorithms. Here, this is a simple cubic structure. Suppose I'm taking the very complex structure here. You can see here. This complex structure, when I'm converting as a STL file, now you can see so many number of triangles on there here. This is a STL file structure as well as the representation of the STL file. Here, nowadays we are using the STL file only. The most common file format is the STL file. Okay, the second most common file format is the .obj. Because in the STL file, we can't save the multicolors, we can't save the multi-materials. So that's why, okay, so many file formats came in the 3D printing technologies. The AMF, okay, the Additive Manufacturing Committee, they are developed a one file format as a AMF. Even Microsoft people, okay, they are developed a one their own file format, that is a 3MF. Still now, okay, this STL and OBG now we are using here. The STL is using for normal only single color printing. Suppose you require the multicolor printing, and that case we are using the .obj file format. Here, how we are good, okay, we are developing the STL file. The STL file is here important in the 3D printing process. The STL file we can develop with using the 3 techniques. First one is that we are going to develop it with using 3D CAD modeling technique. Second one, we can develop with using the CTRM understand data. And third one, we are developing with using the 3D scanning technique data. Here, I'm going to I'm going to give a demo on how we are going to develop a STL file with using the 3D CAD software, as well as how we are going to develop a STL file with using the CTRM understand data in this session. Suppose, okay, this is a Creo software. In this Creo software, how we are going to develop a STL file, I'm showing to you. First, I'm making a simple cube. How the simple cube can convert in the clear software, I will show you. Now you can see this is a simple cube here. Now, first I'm saving this file on the desktop. Now I'm going to convert the STL file. Now save as. And when I'm going to save as here, so many file formats you can see here. Normally for this Creo, the extension is the .prt. For this Creo software, the file extension is .prt. Okay, if you want, you can save as a different file formats. I require the STL file. So now I'm going to save as a STL file. Now you can see STL.stl. Okay, that is called a stereolithography. So even you can save as a OBJ, and you can save as a VRML, and you can save as a AMF file format. Because this AMF and VRML and OBJ and STL, these 4 type of files we can use in our 3D printing technologies. Now I'm going to save this file as STL file. Next, I'm clicking OK. Now you can see here the total each surface is tested with the triangle. Now you can see this surface is splitting into the 2 triangles. Similarly, at the surface. So like that, the 6 faces has 12 surfaces of this cube here. Like that, okay, this is a simple structure. So that's why the total object is divided with only 12 triangles. Suppose I'm taking the very complex structures, how it will be look like, how it will be formed as a STL file. Now you can see here. This is a representation, or this is a conversion of the normal CAD model to the STL file here. Suppose I'm going to make a sphere. When I'm converting a sphere, how it will be look like, you can see. To make a sphere, first we are going for the sketcher, and that we have to create one semicircle. When the semicircle is revolving with the center axis, we can get the sphere. That is a procedure to make a sphere in the CAD model. Okay, here this is a sphere. Now you can see how it is now. It is very smoother and very accurate. Now I'm saving on my desktop. Now I'm converting as a STL file. I'm clicking OK. Now you can see how it will be look like. The total surface is divided. Okay, the total surface is occupied with the triangles. Now you can see the total surface tested with these triangles. Now how it is one. Is it accurate? No. Here you can see here. The previous.
Excuse me, sir.
Tell me.
Once again, can you repeat after the sphere? I just missed it. Sorry,
Okay.
sir.
Okay.
Sorry,
Okay.
sir.
Okay.
Thank you. Only STL formations.
Nothing is there. File. Go to save as. Next. Okay. Here choose the stereolithography. Select as a stereolithography file format. Do you require one more time?
Yeah, from here only, sir. From here.
Okay,
only.
okay,
Yeah.
just click as a STL file. Then click here, OK. Already is there, so that's why it is not. Once again, it is not converting. But okay, like that, it will be found. The total surface is divided with using these triangles here.
Okay.
But now you can see here, it is not good. It is not smoother. Actually, in the previous
Yes.
it is having very smoother. Now you can see here, just see the
Like
outer
mesh.
shape. Yeah.
Yeah. Thank you,
Now,
sir.
yeah. Now I want to convert some of these parameters. I want to make a smoother file. So here, some conversion parameters are available in CAD modeling softwares. Here in the Creo, here chord height, chord angle is there. Similarly, in the different CAD modeling techniques having their own parameters to convert the STL file from the CAD modeling data. So we have to control the parameters, then we can get the accurate model when the surface is uneven and when the surface having the curvature. If the normal plane, if the normal surface, there is no issue. But if it is this type of curve shapes, when we are converting from the CAD modeling to STL file, we have to control the parameters in CAD modeling softwares. Then we can get the accurate data. Suppose I'm going to print this pier. Okay, after completing this 3D modeling, okay, you're not getting the proper shape. So it is not looking like a smoother surface. So for that reason, you have to control in your CAD model. Okay, that is okay. In the earlierly, Dr. Vairov sir explained about these parameters. Okay, how it is the controlling. Okay, the design for additive manufacturing. You have to design according to our additive manufacturing technique. Then we can get our requirements in the 3D printing techniques. That is required here. Suppose I'm going to make a smoother one here. Now, save as. I'm making STL file. Now here some options are available here. The customized export. Then click here, OK. Now here, which file format is required, or binary or ASCII? Okay, normally binary file format we can't read. Okay, we can read ASCII file format. If suppose you want to do some any research, if you want to develop some algorithms, in that case we are using the ASCII file format. And here you can control the chord height and angle control. So whatever the deviation is there from the curvature to this lead line, that deviation is called the chord height. Actually, here we require the curve. But here instead of the curve, when we are converting the STL file with from the CAD model, it will be convert from the curve to the line. When it is converting, some deviation will be occur. The deviation, it is representing the chord height in the Creo software. Not here in any way, almost. Similarly, when the triangle is forming, here it is forming with some angle. So whatever the angle is forming, whatever the angle you can see in the triangulation, that is called the angle control. That you can control in your CAD model, then you can get the accurate model, then you can build a perfect, accurate, smoother 3D printing models. Now in here, normally it is taking automatically 1.8. So instead of 1.8, I'm giving the 1. Now you can see I'm applying here. Now you can observe how it will be transferred. Now you can see here. Previously, compared to previously, this STL file is very good. Okay, now I'm taking now I'm typing a 0. Now it is not taking the 0, it is taking the 0.05. Now the angle also I'm taking the 0, but it is not taking the 0, it is taking the 10 power of -6. That value is taking. Here you can control the step size. The step size means how many number of steps are there. Okay, how many number of divisions are there. How many number of slices are there when converting the CAD model to the STL file. That is representing the step size. Okay, all these things you can control in your CAD modeling packages, CAD modeling softwares. Now I'm choosing the chord height 0.05. I'm choosing the angle control 0. Now I'm applying here. Now you can see how it will be converted. Yeah, now how is it? The previous is the first, how is it? The second, how is it? Now third, how is it now? Yeah. Compared to first stage to the second stage is good. Compared to the second stage to the third stage is very good. So when we are using this type of STL file for our 3D printing machines, then we can get the good and accurate models. Now how, when we are converting the STL file, how this STL file look like? And now you can see in the ASCII file format, file, save as, stereolithography. Now I'm choosing some options, custom exports. Okay, I'm taking a ASCII file format now. Yeah. If suppose I'm taking the 00, there is no issue here because this is everything. Okay, the total object has the surfaces. So if any curvatures or any curvature portion is there, and that we have to change these parameters here. For normal plane surface, it is not required to convert these parameters here. Now you can see how is the STL file format. Now I'm opening with Notepad. This is a structure. This is a STL file format structure here. But the total how many number of triangles are there here? You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the queue has totally 12 triangles. So that's why you can see here 12 triangles here. Next, each triangle consisting of the 3 vertices. That means 3 coordinates here, or 3 points here. Each point consisting with the x coordinate and y coordinate, z coordinate. So each triangle has a facet normal. And like that, the triangle will be represented in the STL file. Then each triangle information you can see in the STL file. This is a representation of the STL file here. And this is a conversion of the STL file with using the CAD modeling technique here. Now, the next one, the first one, how we are going to convert the 3D CAD model to STL, that is finished. The next stage, how we are going to convert the CT to STL file. Now we are going to look in this session. So to convert the CT to MRI scan, we require the first DICO images. Actually, what is the DICO images here? So when we are taking the CT scanning, here the total object, the total body is dividing the number of layers. Suppose you are going to make take a CT scan of your head. Almost your head height is 10 centimeters, suppose. Okay, now it is splitting into the number of layers. Normally for the 64 CT scanner, it is taking 0.625 mm slice thickness. Okay, based on the machine capabilities, it is dividing the number of slice thicknesses. Okay, based on the slice thicknesses, the totally object is divided into number of layers. Suppose you can see here this head when I'm converting, when I'm scanning here, this is the DICO images here. From here to here, suppose this much height, nearly it is taking the 124 image or 124 images taken. So here, this is a process to develop a patient anatomy to the DICO images here. So first we are going to we are taking a scanning of the patient. Then the scanning of the patient raw data we are converting as a DICO images, because DICO images are the standard file format in the radiology community. Okay. These DICO images they can use for the in the different medical aspects in the different medical applications. Okay, these DICO images we are collecting and we are using to convert a STL file. Okay, we require the DICO images. Okay, normally CT raw data we can't convert as a STL file, we can't convert as a CAD model. We require the DICO images, a digital image communication in the medicine. Okay, that is a file for, or that is a full form of the DICO images. That DICO image is required for making a medical model or to convert the STL file here. This is a raw data. Okay, when we are taking the CT image, CT scanning, okay, this type of raw data you can see here. This raw data they are printing in the X-ray report and they are giving to doctors. Okay, based on this printing report, they are going to diagnosis. But for our engineering, for making a medical models, okay, we are going to collect the DICO images. This raw data once again then converting into the number of layers, and this layers information is converting as the DICO images. These DICO images we are going to convert the STL file. This STL file we can use for our 3D printing applications. So how we are converting this CT or MRI images into the STL file, that you can see in this demo. Here, nowadays, so many softwares available in our medical community. One of the software is the 3D Slicer. This is a open source software. You can directly download from the net and you can use yourself. Suppose Mimix is there, that is a commercialized software. For single license, okay, it is around the 25 lakhs. Okay. That is the very costly softwares. This is a 3D Slicer is an open source software. Okay, this you can use to convert the DICO image to the STL file. Now I'm giving us a demo on this 3D Slicer, how we are going to convert the DICO images into the STL file format. Okay, I already forwarded these instructions and DICO images to your email. Okay, you can download this 3D Slicer software from the net and you can install in your laptop and desktop. Then you can practice after completing this session. The first we are going for the low DICOM data. Sorry. Already I have forwarded this DICO images and this 3D Slicer practice instructions and instruction process. All these files I have forwarded through mail. Please check once and you can download, you can practice. Here, this file is consisting on the desktop. Next, I'm importing this DICO images. Okay, now you can see here. Okay, these are the DICO images. Okay, now you can see how many number of images are there. 136 images are there for single mandible here. So for the single skull here. So these diagram images I'm using to convert the diagram image to the STL file. Then click load. For this software, we require the high compatible computer, then we can do easily. Now, go for the volume rendering, next step. Next, go for the volume. Next, enable and display. Now you can see here, these are the patient images, diagram images. This is the raw data. When we are going to scanning, when the CT scan machine, it is collecting this raw data. From this raw data, we are converting diagram images. These diagram images we are using for our medical modeling purpose. Here now you can see here, these are the different diagram images. Here you can see in the different layers you can see in the different direction. This is a top to bottom. Okay, this is the one side to other side. Now you can see here this front to the back. Like that, you get different three views you can see in our medical software. Now here I'm converting from this raw data to the CT data. Okay, we require the bone. Okay, so now here I'm choosing a bone as our required material. Now I'm choosing the CT bone. Here now you can see different options are available. If you want, you can extract the liver. If you want, you can extract the nose. Okay, whatever the information is required, that you can extract from this raw data. Here I'm taking the CT bone. Okay, here now, okay, here you have to adjust these values. Okay, this here the medical committee, it is called as a threshold. We have to apply the threshold value to choose the proper CT bone. Here, whatever the density is there in our mechanical community, similarly in the medical community, threshold value is there. Based on the threshold value, they are choosing the different anatomy. Now, okay, when I'm adjusting this cursor, now you can see how it is going on. Slowly, the soft tissue is going to vanish. Now you can see. Now almost all you can see in the bone over here. When I'm choosing here in this side, okay, now you can see the totally black color is there. That is called the air. Now here you can see this is a bone. Okay, my region of interest is the bone, so that's why I'm selecting a bone. Next, okay, I require only this small portion only. I don't require this remaining portion. I require only this amount only because it is a very big part, and this big part I cannot accommodate in our small 3D printer machine. So that's why I'm removing the unwanted portion. So with using the crop volume, okay, here one option is there in this one, the crop volume. I'm going for the crop volume. In this crop volume, you can adjust the volume. Okay, how we are going to doing the cropping in our normal JPG image. Similarly, here also you can do the cropping in the 3-dimensional. That is possible with using these softwares. Now you have to adjust the volume. How much volume you require, that volume you have to adjust with using these cursors. You have to drag it here. Okay, so I require only this much portion only. This also I'm required only this much portion. I don't require totally. So here, actually, the back side, the spinal cord is there. I don't require the spinal cord. I require only this magazine manual, suppose. So for that, I'm choosing this value here in this case. Here, which type of interpolation is required? Yeah, are you require the linear interpolation or you require the B-spline interpolation? Yeah, here in our CAD techniques, so many type of interpolation techniques are available. One of the techniques are the B-spline and linear. When I'm choosing the B-spline, we can get the accurate. So that's why I'm choosing the B-spline model here to convert the diagram images into the CAD model. Here, I require up to this much. So that's why I'm going to extend here. Then I click apply. When I'm applying here, now you can see how it is going on. Now it's calculating and is going to cropping the volume in each image. So that's why it is taking some time. Now you can see the total image is cropped, and lastly we are getting our required three-dimensional now. Now once again I'm going for the volume rendering, and I'm removing this. I'm disabling this one. Then I'm converting as a CAD model. Next, go for the Legacy editor. These are the sequence of steps is required to convert the diagram images to the STL file. Okay, I have forwarded here one PDF. Okay, or when you are seeing that PDF, easily you can practice yourself. Then I'm clicking as an editor. And now here, I'm going to edit the images. So I crop the images now. That cropped image I'm going to joining. So that is called the editing. Here now, all these images I'm joining with using this edit option here. Then clicking edit, okay. Now here, I want to make a bone, okay. I want to make a bone, maxilla and mandible. So now we here, once again, we are going to take a threshold effect here. Threshold. Now here, which type of bone is required here? Okay, I require the bone. Here, different type of tissues. Here also you can choose. I require the bone. So this is my tissues here. So once again, you have to adjust in this module also. And now here you can see, okay, here totally the volume is selected when I'm choosing this one. So I require only this portion only, okay, this is I don't require here. This is actually soft tissue. So when you are dealing this medical data, some human, you have to know how the human anatomy is there inside of this diagram images. Then you can easily extract, then you can get the 3D CAD model easily. So I'm adjusting these values. Now it is good compared to previous one. Next, apply. Next, go for the make model effect here. Then apply here. Now you can see, okay, this is our CAD model. From this diagram images too, we are convert the CAD model. Here you can see a small errors over there. Here, this is unwanted portion. This is unwanted portion. Okay, you have to spend some time, then you can remove it. Okay, you can get that good quality model. You can see this is a accident case. Okay, almost all the teeth are collapsed. We are going to reconstruct this mandible. So on that case, we are used this diagram images. Okay, this is okay. Now you are converted the CAD model, but okay, we require the STL file. Okay, to print the model in the 3D printing technologies. So we are going to save. So here, what we require here, I want to convert a bone and as STL file. Which type of file format is required? Are you require the OBJ or you require the STL file? Yeah, or you require the polylines. Okay, with using the polylines, you can construct the surface from surface to solid. Okay, like that, some softwares are available. So on that case, they are using the polylines. So here I'm using, I wanted to print this STL file with our 3D printing. So that's why I'm choosing as STL file here. Now where it should save. So that path also you have to give here. So desktop, I'm choosing the desktop. Then save here. Now you can see this is a bone. Okay, that is we are saved here. Okay, now I'm opening with a normal lay. Okay, anyhow, these are the 3D printing softwares. Here, this is a 3D printing machine softwares here. Now here, how we are going to print the model here. Okay, now I'm okay after converting the STL file. Okay, I'm calling into the 3D printing software. So here, this is a one 3D printing software here. Okay, this is the Flash Forge. In our FST, okay, in our university, we are having the 2 3D printers based on this Flash Forge company. So they are provided this Flash print software. Okay, this is a Flash print software is the intermediate software to convert the STL file to the sizing information. Now you can see this is our STL file. Okay. From the diagram images to we convert the as a STL file format in the with using the 3D slicer software here. This is the 3D printing software. Why we require the 3D printing softwares here? The 3D printing software is using to convert the STL file to the sizing information. Okay, next one. Okay, the third method is okay. The 3D CAD model to STL file is over. CTMR scan to STL file is over. Next, 3D object design system to STL file. How they are going to convert the point data to CAD model that you can see here. Here, majorly this type of techniques is using in the reverse engineering. Suppose I want to make this model, okay, this model to CAD model, the physical model to the virtual model, they are using the reverse engineering technique here. For in the reverse engineering technique, they are using the 3D scanning devices here. They are using the 3D scanning devices here. This is a 3D scanner. With using the 3D scanner, we can capture the data here. Okay, we are capturing the only outer surface point cloud data only we can capture. But okay, directly we can't make a physical model with using this point cloud data. Once again, this point cloud data to we have to convert the surface. From the surface to we have to convert the solid. From solid to we have to convert the STL file. That STL file you can use for 3D printing. Then you can make a model. So here we require some softwares. The conversion software is required. Here tomorrow we are going to demonstrate here one 3D scanning machine. Okay, how we are going to capture the data on physical object. That is, we are going to show tomorrow demo session. Here, after collecting the information, how we are going to convert the point cloud point cloud data to the STL file that you can see in a small video here. This is a 3D scanner. With using the 3D scanner, okay, they are capturing the data. This is the point cloud data. You can see here. This is the data. Now you can see for this totally to convert this to capture this data, it is required nearly 5-6 hours. Thereafter, okay, this is this point cloud data is not good. Here so many pore structures are there, and here the totally surface is not constructed properly. So here the second stage, you have to do the watertight mesh. Okay, here this mesh is not constructed properly. So we have to construct the mesh properly. That is called a watertight model. That watertight model we are going to do in this software here. Okay, that is we are going for the Geomagic software here. Okay, the totally pan cloud data, they are exporting the Geomagic software. In this Geomagic software, you can do the watertight model. So whatever the unwanted objects are, that is they are going to deleting, and the holes are filling. Now you can see, okay, this is okay. When we are capturing the data with using the with using this 3D scanner, we are not getting proper information. So we are going to edit. Okay, that's why we are using this software. Okay, now we are going to convert the surface with using the knobs, non-information B-spines, with using this point cloud data in this Geomagic software. Now the features are extracting. Okay, here we are going to convert the exactly roundness, exactly surfaceness, and exactly flatness. All these things we are going to do in the Geomagic software with using the surface model. Now they are the surface data. Okay, once again, okay, they are converting in the solid edge software. In the solid edge software, okay, we can convert the surface data to the solid data. In the in the reverse engineering, okay, with using the 3D scanner, we can get only point cloud data. From the point cloud data to, they are extracted the surface data with using the Geomagic software. Thereafter, the surface data to, they are converting a solid data with using this solid edge software here. That once again adding the features. Okay, they are making a roundness and making a flatness. All these things they are extracting with using this solid edge software. Then okay, lastly they got the 3D CAD model from the point cloud data. This CAD model we can convert STL file. That STL file we can use for our 3D printing technologies. Now you can see here, if you want to make a reverse engineering, how many softwares are required? Simply we are collecting the point cloud data from the 3D scanner. But this point cloud data to surface, we require the Geomagics. From surface to solid, we require the solid edge software. Like the softwares are required. Without softwares, without CAD modeling techniques, we can't do anything in the 3D printing industry, in the 3D printing technologies. Now you can see here, okay, with using the CAD modeling technique, with using the CTR-MRS scan data, with using the reverse engineering techniques, okay, we are developing the STL files. This STL file, okay, we are going to do the STL treatment softwares, because okay, suppose okay, when I'm converting the medical data, okay, it is not good. Okay, some errors are there. If suppose okay, those who are creating the civil CAD with using their softwares, okay, those who are working in the architect department, there is the different softwares. Okay, when we are converting that model to this STL file, some errors will be occur. That errors also you have to rectify with using the STL treatment softwares. Okay, here we require the STL file treatment. For that also we require using some magic softwares. We are using some mesh mixture software. So many softwares available in the industry. So we have to reduce the errors in the STL file. Okay, when we are converting the surface to the STL file, so many errors will be occur. Okay, those who are known for the Chu and CK book, the chapter 6 is dealing all these things only. Okay, then after treatment of the STL file, okay, you have to import in the AM softwares, 3D printing softwares. On the 3D printing software, you can add the support structures and you can do the slicing. That slice information we are giving to the AM machine. Now you can see here, almost all these things we require the softwares here. Okay. The AM machine, it is taking the layer information. Okay, based on the layer information, it is constructing the model here. Here now I'm going to show you a small demo how we are going to generate a supports, how we are going to convert the STL file to the slice information, and how we are going to generate the G code. That G code we are giving the FDM machines. The different machines having their own softwares. So almost all the generalized software is the Cura software. Okay, there is an open source software. So that's why I'm giving a demo on the Cura software for understanding the concepts of the 3D printing. So support structures as well as orientation of the part on the build platform. Okay, here this is a Cura software. This is open source software. Okay, nowadays, okay, this Cura is using for so many machines. Okay, first initially, okay, we have to import our STL file into Cura software, into the 3D printing softwares. Now I'm operating so many softwares, so that's why it is taking some time. Okay, already one STL file I have forwarded to you with through mail. Okay, that STL file I'm importing in this 3D printing software. Now it is loading in the software. Okay. Actually, okay, this is a very big model. Actually, our machine is only having this much capacity. Okay, or you can pull with using this cursor or this with using these arrows. This is x-axis. Okay, this is y-axis. This is z-axis. Okay, with using this arrows, you can adjust the STL file in the build platform. This is build platform. Okay, here I suppose I'm using the Ultimaker. In the morning session, Dr. Srira Venkatesa yes, informed to you, okay, they are having their Ultimaker machine. Okay, that is around cost for 5 lakhs. For that, okay, they are using this Ultimaker software. This is an open source software here. So, okay, this is very big. Okay, this is mission capable build platform is very less. So on that, you can do the scaling. Okay, that features are available in this 3D printing software. Okay, now I'm doing the uniform scaling. Now I'm reducing the 10%. And now you can see here. Now you can increase, you can decrease. Okay, you can change the values here. You can do the scaling with using this option. Okay, that is also available in this Ultimaker Cura in the 3D printing softwares. Then I'm going to place this model in our build platform. It is adjusted. Now you can see the total color is changed. Okay, when the yellow color is coming means then okay, the model or the software can print, that is indicating of this color. Now here, now you can see here different type of support structures also we can develop. Normally we are using the PLA material. Okay, whatever the file, the uniform slicing, okay, the totally this model, the STL file is divided into the number of layers. That layers we are going to use for our 3D printing technologies. Now you can see here how it's going on here. I'm operating with so different softwares, that's why it is going on like this. Now you can see here, now this is a sequence of steps how the data is transferring from the 3D CAD model to this slicing information. And now this 3D CAD model, now we are converting the STL file. Okay, with using the slicing softwares, with using the 3D printing softwares, we are converting this STL to the number of layers. Now you can see how it is converting this model to this model. This layer information we are sending to the 3D printer. Based on this layers information, the machine will build the model here. This is a CAD. Okay, this is a STL file. Now you can see this STL file. When we are going to the slicing, now you can see this is the number of layers. You can see the total file. It is dividing into the number of layers with using the Z-axis. And the Z-axis is going to do the slicing. It is going to dividing the number of layers. Okay, now the bottom layer is taking and printing. Next n-1 layer, n-2 layer, like that it is taking from the bottom to the top. This based on this layer information, the 3D printer nozzle or 3D printer laser or 3D printing Z or the head will be moved based on this layer information. This layers information you have to create, you have to develop with using our 3D printing softwares. Okay, one of the software is Cura, where there is an open source software here. Now you can see this is how much thickness is required. Okay, what is this layer thickness is required, that you can see. If we are choosing the very less thickness, it is taking so much time. If we're taking the higher thickness, it is taking less time, but the strength is very less. Okay, you have to compromise. You have to, are you require the strength? Are you require the quality? That you have to choose yourself. And here in the morning infill, okay, the Sridhar Venkateswara has explained about this infill. And yesterday, Dr. Vairakumar also explained the theoretical part, infill. The percentage of the metal is filling inside of the layer. That is called the infill. That also you can adjust here. Like that. Okay, so many options are available here that you can extract, you can do that one. That is, you have to adjust. That is called the bull parameters. Okay, here in this one already you have seen the sequence of steps. The CAD model STL file transfer to the machine. After converting down, next we have to set up the machine setup. Whatever the machine setup is required, that you have to do in this 3D printing software. After setting all these parameters, all these things, now you are going to develop this. Here, so many parameters are also available. Okay, what is the quality? Okay, which much layer thickness is required? Which types shells you can take when it is printing? And what is the infill percentage? Which type of materials you are using? What is the temperature? That also you can control. The build platform temperature, and how much speed that it is the nozzle it is taking to print the model. That also you can control. All these things you can control with using this 3D printing software. Here for the different 3D printing machine, suppose the different 3D printing softwares. But the total overall intention, overall idea is same this one. Okay, they are setting the machine parameters, and that after setting the machine parameters, the total STL is converting the slices. That slices information they are sending to the machine. Based on the slice information, the machine will build the model. That is the concept of the 3D printing technologies. Now I'm going to slicing here. Now it is going to processing. Now you can see the bottom layer to top layer. You can see here, this is the first layer. Top layer. Now coming down. These are the different layers. Now you can see here how the total object is divided into the number of layers. Okay, this is the bottom layer, first layer. It will be printed like that. Next, second layer, third layer, fourth layer, like that. It is printing. Lastly, we are getting our required object. Now here you can see here how we are going to develop a suppose. Which type of suppose you can see, okay, in your STL file that you can see here. I'm taking same STL file in the software. In the Curio software, we can't see perfectly about the suppose. In the software, you can see easily the suppose structures. The same problem. Actually, this is a big model. Our build volume is very less. Now we are going to do scaling here. Suppose you can rotate, you can place, you can rearrange this one on the build platform. And that is possible with using this 3D printing software. Okay, this is called the orientation. How you are placing how you are placing this STL file on the build platform, that is indicating the part orientation. Suppose I'm taking this is my part orientation. How the suppose will be built. Now you can see here, I'm taking the suppose. Because when I'm printing this layer, this bottom, okay, this top, okay, this layer, without the support, we can't print. So that's why we require the support structures. How the support will be generated, now you can see here. You can see how the supports are coming. Only a small support is required here. Here, okay, this, okay, here only required. With using the small supports, you can place here. Even the suppose also a different type of suppose over there, the teak and linear. It is taking the teak type, it is taking like that. Suppose same structure, I'm using the linear suppose structures. Now you can see how it is going on here. Now you can see these are linear suppose. You have linear suppose. Here once again, okay, like that, okay, with different type of suppose structures you can use, you can place, okay, where is required, like that. Okay, after using the after generating the suppose structures, now you are going for the printing. Okay, without suppose we can't do. Okay, in the design for additive manufacturing, it is telling that you have to choose the different orientation to reduce the suppose structures as well as increasing the structure, increasing the strength and improving the surface quality of the 3D printed component that is required. That is during the design for additive manufacturing. And then, okay, you have to take care about all these parameters when you are placing this STL file on the build platform. Now I'm taking the print. Now you can see which type of material is required. That also it is asking, and which type of options is required. Okay, is it required the shell type? Which type of shells are required? How much infill percentage? Okay, when it is going the inside, okay, which type of shape is required? Okay, nowadays so many algorithms are coming based on this infill percentage and shells types, all these things. And how much speed is required? How much temperature you have to set up? All these things you can give. These are the machine parameters. After giving these machine parameters, okay, automatically the G code will be generated. And now the G code I'm generating on my desktop. Now you can see how it is going to do the slicing here. Now you can see the slicing the model. Okay, this, okay, for this object is taking 3 hours. So now I'm taking the layers information out here. For this object, it is taking the 284 layers. So what is my bottom layer? Now you can see here. This is my first layer. Now the second layer, third layer, fourth layer, like that. The different layers it is going on here. Now here I'm telling the infill percentage. So here, when it is printing the model, first it is taking the contour of the object, and the between it is taking the different infills. Okay, I'm choosing the hexagonal infill. So that's why here hexagonal shapes you can see here. Suppose you are choosing the linear, you can not directly lines are coming. Here nowadays so many different type of shapes you can choose, okay, with using the different softwares. And now how much infill percentage, how much density is required? I'm choosing the 30%. Total only here, remaining 70% is the halo. Only 30% material is there inside. Like that, you can choose with using the infill percentage values. You can choose this structures inside of the inside of this boundary. Okay, this is my outer boundary. First, it is taking the outer boundary, then filling the model inside here. And that is a process to print here one layer. Then next layer. Now you can see here. And now you can see the different layers here. Like that, next layer, next layer, next layer, like that. Just printing. Okay, now you can see these are hexagonal shapes here. And this is totally. Oh, I'm choosing only 30% infill. The totally 70% is halo. I want just look this model. I don't require any strength. That's why I'm choosing this 30% infill. Suppose you require the strength, you have to choose the 100% infill. Okay, that is your wish. Okay, based upon your application, you have to choose the infill percentage and structure of this shape. Okay, now you can, okay, now this G code we are developed that you can see on desktop. Save file. Where it is saved, program, STL file. Okay, once again, I'm saving this file. Where it is saved, I don't know. Okay, demo 3D printing. It also is not saved. Print. Okay, it is going to print here. I'm selecting the G code on desktop. Oh. Now you can see here. I'm opening with my note with Notepad. And this is the G code. Now you can see starting the G code M140, M104. Okay, all of those who are dealing like CAD/CAM subject, they can understood. They say about the M codes and G codes. What is the speed is required? What is the speed is required? All this. What is the layer information? All this information you can see in the G code. Based on this, okay, this G code we are sending to the machine. Based on this G code, the FDM printer will be print the model. Okay, this is about your STL your demo session on STL file as well as demo on the 3D printing softwares. Any questions regarding this topic? You can ask.
Good evening, sir.
Yes, sir.
Yes, sir. I have one doubt, sir.
Yeah, sir.
What is the meaning and of this generative design regarding this TFAM?
Generative design. Okay. We are going to do some topology optimizations actually. Okay, suppose the same object, we are decreasing the material and increasing the strength.
Okay.
So for that, we are using the different type of technologies. Okay, here one of the technique is the topology optimization. Okay, with using the topology optimization, we are going to generating the redesign. We are redesigning the model based upon our normal design. So that is called the redesign.
Reducing the material.
Yes, sir. Reducing the material as well as increasing the strength.
So, for TFAM, it is common for all kind of 3D printing machines. For example, if it is a metal printer or cellular type, the design concepts are same, right?
Yes, sir. Design concepts are the same. So that's why nowadays when we are going for the MS program, okay, design for additive manufacturing subject is there.
Thank you.
Okay, sir. Thank you.
Sir, am I audible?
Yeah, yes, sir. You're audible.
Really interesting thing that I want to tell you. I mean, got some knowledge about this, but the problem is that you told once during your lecture that that the compatibility issues of computer is really a problematic one.
Because actually, sir, now I'm operated 4-5 software, sir, at a time. So that's why this issues came.
Yeah. No. I'm talking about a 64-bit computer is a minimum necessity.
Yes, sir. Yes.
32-bit computer won't do.
Yes, sir.
In fact, I tried to install the thing, the software. The softwares have been installed, but it's not opening.
Yes,
graphics incapability.
Yes, sir. Yes, sir.
So these issues come, and that's why we need a high configuration of a computer to run these softwares.
Yes, sir. Yes, sir. Actually, this medical softwares, it is taking so much data actually.
Yes, otherwise
when we are using the medical softwares, we have to use the higher compatible software and higher level computer.
Otherwise, the thing is very, very interesting, and I would request you if you can send us the recorded version of your session.
Yes, sir. Definitely, I will send to you.
It will be very beneficial.
Yes, so that's why I have forwarded this PDF files.
Yes, that we have got. Yes,
but when you are seeing that PDF files, you can do practice yourself. So that's why I have already used that.
Still, your lecture is very, very valuable, and I would like to have that as a recorded video.
Yeah, definitely. I will share to all the participants.
Yes. Okay. Thank you, sir.
Thank you, sir. Those who are interested to do the practice, we can do the practice now. Yeah, I will guide you up to 4 or 4:15. Yeah, Bhagyo sir, I will provide this PPT only. In this PPT, only 4 or 5 slides are there. Nothing is there. Definitely, I will provide you this PPT. So what about the strings? Control strings. How to control strings in the 3D printed parts?
And one more thing, sir.
Yes, sir.
The softwares are machine specific, as you told.
Yes, sir.
That means this Cura software
Yeah.
may not be enough for a particular machine.
Yes, sir. Yes, sir.
So there are some limitations as far as the software is concerned, because you cannot use any software for any 3D printer machine.
Yes, sir. That's why I'm telling to you now. Okay. Different 3D printing providers, they are providing the different 3D printing softwares. But concept is same. Suppose Creo is there. So okay, CATIA is there, and SolidWorks are there. These are the different 3D CAD modeling softwares. But the scenario and the sequence are the same. Okay. Suppose if you want to do the extrude, the same options you are using in the Creo as well as in the SolidWorks.
Yes.
So that's why I'm telling you, okay, this is a procedure, but the procedures, the sequence of the steps are the different in the different softwares. Even nowadays, nearly 100 of the 3D printing softwares are there. Okay, different vendors, they are using the different 3D printing softwares. Here you can see in the Cura, we can't see the support structures perfectly. Suppose in the Flash Forge, you can see the support structures perfectly. Okay, here, different vendors, they are using their own capabilities.
One more query, sir.
Yes, sir.
While printing on the platform,
yes, sir.
If the part is, if the part can be oriented in a flat position,
yes, sir.
Then what is the need of tilting it and providing support structures to the part?
Sir,
is there any need? Is there any need?
Yes, sir, definitely. Okay, sir. To build the model, it is directly not sticking to the build platform. Here, intermediate some 2-3 layers is taking from the build platform to our required object. First one. Second one, we have to avoid the support structures to improve the surface quality of our 3D printed component. Hello, sir.
Yes, I did not get the thing completely, because you the part which you showed,
yes, sir.
Part which you have shown us,
yes, sir.
That was lying flat on the build platform.
Yes, sir. Yes, sir.
And the printing took place. I mean,
yes,
the part was built up.
Yes, sir.
And then on another, another software, Flash Print probably, you tilted the part.
Yeah. So actually, okay, here we require only flat one is a better. But in the different CAD models and the different parts, we have to change the orientation to avoid the support structures. You have to play. You have to play with your 3D printing softwares.
Okay.
You have to avoid the support structures. You have to reduce the time of the build. That means, okay, how you have to reduce the time to build the model in your 3D printing. You have to reduce the material. That is, you have to control with using this 3D printing softwares when you are placing the different orientation.
Okay.
That you have to ensure, that you have to control. Okay, that you can control in this 3D printing softwares. Okay, this is called the design for additive manufacturing. You have to design according to our missions.
Yeah. Right. Thank you.